So let's take a look at Prim's algorithm. In this example here, I've done a slight modification to our graph class. Basically, I have still the same number of vertices, but I've slightly adjusted our adjacency list and add edges, basically to create an undirected graph in this case. And we're creating adjacencies where the entry in the adjacency list is the main node, and then the things that it's adjacent to are going to be appended onto it, as well as their actual weight themselves. So as I mentioned, basically Prim's algorithm starts at any sort of node. It then starts to pick the smallest possible values until it arrives at a minimum spanning tree. Now, one of the main questions that we have here is how do we actually create the actual setup of smallest to largest storage of the edges? We saw that in Kruskal's algorithm. Basically, the way that we did this was we sorted it from smallest to largest. With Prim's algorithm, it actually is very helpful to use something like a priority queue for this kind of storage. Basically, we can iterate similar to where we would see with a level order traversal, where we just add things to the queue as we go. If you remember, we were basically doing that process. We would visit a node, we add its adjacencies onto the queue, and then we can pop them off in priority order, right? So it makes a lot of sense to use a priority queue. Now, in this example here, I'm going to use Python's built-in priority queue. The main reason for that is because it allows us to be a bit more, unstructured with the way that we're storing our data. With my priority queue, it was really just integer values. With Python's priority queue, I can store, say, actual nodes with their weights and say priority based on weight. So it gives us a lot more generality on the actual structure itself. The way that we set this up is we set up a blank list that's going to act as our priority queue. And we start with a source, and the source is going to be, in this case, I'm going to say node 0. So I'm going to start at node 0. And basically, one of the main things that we're going to do for each of these is we're actually going to do something a little bit different from what we showed in the actual previous video, is we're going to set up this key array, which is going to have everything set to the theoretical maximum size. Basically, the main idea of this is we're going to assume that everything has an infinite distance between itself and our source. And as we unveil more things, we'll update with their actual weights. That's going to allow us to avoid actually picking something that we haven't seen yet, right? So that's the way that we're generally maintaining that idea. We're also going to have still our parent, which is basically going to indicate if something's been picked or not. -1 indicates that it hasn't been picked, so we'll update that as we go to determine where it was picked and what it's connected to, essentially, right? And then we have in MST, which is going to tell us if a node is currently in our minimum spanning tree or not. So we'll create an entry for each of our vertices and set that equal to false to start. From here, we simply are going to push onto our heap, which we do using a heap push. Heap push takes in first the list that we want to use, which is the PQ list that I created. And then it takes in the value that we're working with, which is going to be 0, which is the weight, and then source, which is the node itself. So source is the node, 0 is the weight. We're basically saying the distance from source to itself is 0, right? So we've already reached it. That's where we're starting. Then all we do is we just say, well, we have things in our priority queue. We're going to do the following operations. We're going to set u equal to the value of the current top of the priority queue or front of it. So we're going to do a heap pop, as Python calls it. And we're going to get the value index 1, right? And we're basically just going to say if this is not in the MST, right? So if it's not in the MST yet, right? Then what we're going to say is we're going to set in MST to true. So we're going to add it into our minimum spanning tree. And then what we're going to do is we're going to say for all of the things that are adjacent to the node that we just picked, if they're not in the MST, right? And if the key is greater than W, then we're going to update key of V to be equal to W. We're then going to go ahead and push onto the heap those values. So we're going to push onto the heap the value that we just saw, which is key of V and V. And then we're going to set the parent of V equal to U. Finally, at the end of this, we just return parent and we're done. So just to explain this in a bit more detail, basically we're saying if the node that we have visited is not in the minimum spanning tree and if the key value that we currently have for it is bigger than the weight that we have just retrieved, so basically if every single other one that we've seen so far that connects to this node is larger than the one that we're currently at, we then set that to be the new smallest one that we've seen, right? So basically just tracking the smallest possible connection to each node each time, and then as we go, we construct out our minimum spanning tree through this process, right? So just to show you an example of this, I have a graph with 5 vertices with some various different connections and weights associated with it. And just to show you, basically, we can call Prim's algorithm and get back the parent. And then there's a special way that we have to basically print this out. Basically, we just map the parent at I to the actual index I itself. And what you'll see here is basically this sort of process where we actually get back the minimum spanning tree. So if we do chapter 11 prim.py, you'll see that the minimum spanning tree for this graph here is we go from 0 to 1 with a weight of 2. We then go to 1 to 2 with a weight of 3. We go 0 to 3 with a weight of 6. And then we go 1 to 4 with a weight of 5. And you can take a look and verify that this truly is the minimum spanning tree for this graph. And you'll find that it is generally the best solution that we have in this particular situation. So then the question is, what is the time complexity of prims, when we compare it to Kruskal's? And the idea is that it's going to be about v plus e log of v. So you see that this one primarily scales based on number of vertices, whereas Kruskal's primarily scales on the number of edges, right? So this is the main thing that we're considering based on these, right? With Kruskal's, it scales based on the number of edges. So generally, if we have less edges, Kruskal is going to perform better. As edges start to increase a lot, Kruskal starts to perform a little bit worse. With Prim's algorithm, the main contributors to growth are generally going to be, primarily out of the vertices, since there's 2 terms for the vertices itself. Edges still contribute to it, but they contribute a little bit less. So generally, lots of vertices and lots of edges, Prim's is going to, generally slow down a little bit. But, if we can scale down the number of vertices, then we generally have a bit of a better performance. So these are just some different things to consider when we're considering these 2 algorithms, is how they're generally scaling comparative to each other. So this is the idea of Prim's algorithm, and this gives you the basic implementation for Prim's for this particular use case. So thanks so much for watching, and I'll see you in the next video.